As you can see, this video covers section 5.2, the definite integral. The definite integral. So we started talking about the idea behind the definite integral in section 5.1 when we investigated how to find the area under a curve. We left off in section 5.1 with the definition that said area equals the limit as n approaches infinity of r sub n. And again, we picked right-hand endpoints because our book follows the convention of starting with right-hand endpoints. It could have been left-hand endpoints. It's just right-hand endpoints because that's the way our book chose to go. And what we said was that this was equal to a sum of n rectangles added together, and then we took the limit of that sum. That's what r sub n was. We said this was the limit as n approached infinity, and we wrote it as the width of the rectangle written as delta x times the height of the rectangle written as f of x sub 1 plus the width of the second rectangle, again written as delta x, times the height of the second rectangle written as f of x sub 2, plus, and we did this until we got to the width of the last rectangle, delta x, times the height of the last rectangle, which was f of x sub n. This was our concluding statement in section 5.1. We said, well, if we want to find the area, we add up all the rectangles, and then we let the number of rectangles go to infinity. Now, from here, we're going to go into the definition of the definite integral. The issue, the challenge, whatever word we want to use here, is the length of the definition. It's not the complexity of what we're going to write, it's the magnitude of the amount of information contained in the definition that adds complexity to this. So I'm going to go through the definition slowly, piece by piece, and I'll probably change colors as I write the definition to show you that each phrase stands alone, and if we can understand each phrase, then we can put the entire definition together and come to a unified idea of what do we mean by the definite integral. So this is going to be our definition of the definite integral. And again, it's going to fill up the rest of this whiteboard. There's going to be a lot that we're going to write, but again, each individual phrase, if we can come to a clear understanding of what that phrase means, then we're going to be okay when it comes to understanding this definition. So it begins and it says, if f is a function defined for a is less or equal to x, less than or equal to b. All right, so we're going to pause now. And if you're following along in your textbook, you'll see that we haven't written very much of this definition. So let's pay attention to what this says. F is a function. We're not surprised by that. But what's missing here, right? What word is not here? The word that's not here is continuous. Continuous is not here. It does say f is defined for all the x's between a and b. All right? So there are no holes in our function. There are no vertical asymptotes between a and b. But because we have not specifically said continuity, we've said defined everywhere between a and b, we've opened the door to the possibility that we could have a jump. There could be a jump here. There is not a vertical asymptote. There is not a vertical asymptote. And there's not a hole. We don't have a hole. We're defined everywhere between A and B. But we could have a jump. So the first thing I want to pay attention to is the fact that the word continuous is not included there. All right? And then where do we go from there? It says we divide the interval. We'll change colors now because we're onto a new phrase. We divide the interval. All right, we divide the interval AB into n subintervals. All right, of equal width. And we're going to call that width delta x. And you and I already know what that width is going to be. That's going to be b minus a over n. I'm going to pause there because we've completed our first sentence of our definition. So we have a function. We've talked about the nature of our function. It's not necessarily continuous, but it certainly doesn't have a vertical asymptote and it doesn't have a hole. And what are we going to do with this interval from A to B? We're going to treat it just like we treated the interval from A to B back in section 5.1. We're going to divide that interval into n subintervals, just like we did in the example with the parabola in the previous video on 5.1. And those intervals are going to have an equal width. And their width, we're going to call that delta x, just like we did up here back from 5.1. We're going to say delta x is equal to the width divided by the number of intervals. Right? And that's the way we wrote it in the video in 5.1. We literally wrote that as the numerator was the length of the interval and the denominator was the number of subintervals. And that's what we're doing here. We're just using symbols instead of words. All right? Now we begin the next sentence. We let x sub 0, which is going to equal a, x sub 1, x sub 2, all the way to x sub n, which is going to equal v. Be the endpoints of our subintervals. Right. So at this point, perhaps at this point we should make a little sketch. All right. I'm gonna add a sketch down here just so we can tie into what's being told to us in this definition. So what do we have? We have an interval that starts at A and ends at B. Right? That's what they've told us. It starts at A and it ends at B. Our interval goes from A to B. And above that interval, we have some function. And we'll just draw our function like this. And our function is f. Now, they have given us some information about what we're going to do. That's all we've talked about so far is what we're going to do with our interval from A to B. And they have told us very specifically what we're going to do. They've said, well, you're going to call this beginning point x naught. Right? That's what they said. We're going to call our beginning point x naught. And then we're going to subdivide this interval. And the next value we are going to come across on the x-axis is going to be x1. The next value we're going to come across on the x-axis is going to be x sub 2. the next value is going to be x sub 3. And we're going to continue to do that until we get to the last value, b, down here at the end, and we're going to call that x sub n. We refer to this as partitioning the interval. We are cutting it up into parts. So we let x sub 0, x sub 1, x sub 2, x sub n, which equals b, and x sub 0 is a, be the endpoints of our subintervals. So all we've done is sliced our interval along the x-axis into n equal size pieces. That's all we've done so far. And we haven't done anything else. If we continue, it says, and we let. And now here our notation is going to get a little confusing, but just write it down. I'll make it clear. We let x sub 1 star, x sub 2 star, x sub 3 star, all the way to x sub n star be any sample points in these subintervals. All right, so let's pause again and let's consider what we've been asked to do here. What have they asked us to do? They have said, within this interval from x sub 0 to x sub 1, I'm going to choose a point arbitrarily. You get to pick it. It's not defined by any pattern or any preconceived idea. You can pick any point in here you want. And we're going to call that point x sub 1 star. Meaning it is an x value. It comes from my first interval, and it's a sample point. That's what the star means. It's a sample point. It's not my end point, x sub 1. It's any number. If this is 0 and this is 1, hypothetically speaking, if my interval went from 0 to 1, you could pick any number between 0 and 1 you want. The choice is completely up to you. It is your choice. Pick it. Okay? Now, why are they doing that to us? When in the previous section in the homework, they were very, very specific about what point we should pick. Right? They told us you should pick the right-hand endpoint, the left-hand endpoint, maybe you should pick the midpoint. They were very specific about which point we were allowed to utilize. So why have they now, in the definition, freed us from that constraint of using a left-hand endpoint, a right-hand endpoint, a midpoint? Why have they opened the door to the use of any point? Well, I'm going to draw a quick sketch right here. We're going to erase it to make room for the rest of our definition. But I'm going to draw a quick sketch and try to justify for you why we are allowed to pick any point we want. All right? So let's just blow up this interval right here. This interval starts at x sub 0 and it ends at x sub 1. Right? It goes from x sub 0 to x sub 1. And what our author is telling us is this, our function, right? Our function has some kind of a gentle arc across here. And our author is telling us you can pick any point in here you want. You do not have to pick the left-hand endpoint and make your rectangle that tall. You do not have to pick the right-hand endpoint and make your rectangle that tall. You can pick any point. And that flies in the face of what we want to think about as being rational thought. Because We know if we pick this endpoint, we're going to get a rectangle that's only this high. But if I pick the right-hand endpoint, I'm going to get a rectangle that's this high. And when we look at these two rectangles, we think to ourselves, that is a lot of difference between those two. Likewise, you're freeing me up to pick any arbitrary point. You know, if I choose this as my x1, because I'm in interval 1, x1 star, because I'm freed up to pick any point, if I'm allowed to pick any point, I'm going to get this orange rectangle right here. And there's a big difference between the orange rectangle, the green rectangle, and the blue rectangle. So how is it that I am absolutely freed up and not required to pick a specific point within this interval? Well, it comes down to us remembering this piece right here, this. We have to remember this. We're taking the limit as n goes to infinity. So in reality, our picture doesn't look like this. We're letting the number of rectangles grow without bound. This, yes, this is a sketch of this. But it doesn't really tell us the truth. The truth is, our sketch really doesn't even look like this. As the number of rectangles grows without bound, this width, if we look right here, as n gets bigger and bigger and bigger, our width gets smaller and smaller and smaller. Now, what does that mean to us? Well, it means our picture doesn't really look like this. Our picture really looks like this. And I know that's nothing but a dash on your screen, but what am I trying to say? What I'm trying to say is x of 0 is here and x of 1 is there. And in reality, when your function goes shooting across that tiny little interval, it's essentially going to be flat. Now, I know it has a curve to it, but what I'm saying is, as this interval gets more and more and more narrow, the difference between the height on the left-hand side and the height on the right-hand side becomes almost insignificant. That graph would have to be infinitely steep before an infinitely thin interval is going to have a distinguishable difference between the value or the height at one side versus the height at the other side. So what your author is telling us here in this flat phrase is he's getting to that point without really explaining it in detail. He's expecting us to have assimilated this knowledge and to have come to the conclusion ourselves. What he's telling us is he's clearly stating this interval is so small because we're letting the number of intervals go to infinity, and we have a finite length here. We're going from A to B. That's finite on the number line. Maybe it's 2 to 10. Maybe it's 5 to 5,000. Maybe it's 0 to 1. It is a finite length. And because it is a finite length, and because we're letting the number of rectangles grow without bound, the width of those rectangles is becoming infinitesimally small. It's becoming tiny. So the difference between any functional value is going to become almost indistinguishable. So what he's saying is, if you really want to blow this thing up and look at it clearly, because it is really, in reality, so narrow, your function is essentially straight going across here. And you can see that if you have a graphing calculator, all you have to do is keep zooming in and zooming in and zooming in. Just graph sine or a parabola and just continue to zoom, 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 zoom. Make the interval smaller and smaller and smaller. And eventually your graphing calculator is going to tell you that there's a line going across the screen. Now we know there's not a line, but because the gap, the interval on the x-axis is so small, the difference between the left-hand side and the right-hand side is going to be practically indistinguishable. Hence, your author is saying you can pick any number in the interval you want. You're essentially going to get the same height everywhere. Okay? So let me erase this, get this out of our way so we can finish up our definition. So I hope that explains to you why the definition says, and we let x of 1 star, x of 2 star, all the way to x of n star be any sample point. So let's go back. Now, it's been a while since we were talking about the definition, so let's go back and pick it up from the beginning and just make sure we are all still flowing through this as one contiguous explanation. If f is a function, so we have a function, it's defined everywhere between a and b, similar to our picture here. We've divided our interval, this is our interval from a to b, and we've divided it into n equal width subintervals. We have named these endpoints, and we've enumerated them in a logical manner. We named our first endpoint x of 0, the one that comes after that, x of 1, followed by x of 2, x of 3, all the way to x of n. And now within each of these intervals, we have allowed ourselves to choose any point we want. x1, x2, x3. x1 comes from the first interval, x2 comes from the second, x3 star comes from the third. We've allowed ourselves to choose any point we want. And why have we done that? Well, he's first going to explain to us what each of these notations means. Now, we've already talked about that in pretty good detail, but in the definition, he goes on and he says, so how are you going to choose these? So x of I star, okay, the ith person in this list, the ith value in this list lies in the ith subinterval. And then he tells us what the ith subinterval is. He says, well, that's the interval that goes from x sub I minus 1 to x sub I. So what is he saying to us then? He's saying down the road down here, we reach some number x sub I minus 1. And next to that, one more over becomes x sub I. And he tells us x sub I star lies between here and here. All right, that's what he's saying. He's saying somewhere in here is x sub I star. Now, if that's confusing, and sometimes it can be with these subscripts, I minus 1, I, we can get a little confused. Let's go back to the beginning. Where does x sub 1 live? Well, we said x sub 1 lives in here somewhere, so we'll just pick this as our x sub 1 star right here. Well, if we take a look at this, x sub 1 lives between x sub 0 and x sub 1. Sorry, let me restate that. X sub 1 star lives between x sub 0 and x sub 1. X sub 2 star, we'll pick this as our x sub 2 star. X sub 2 star lives between x sub 1 and x sub 2. And that means x sub 3 star, we'll pick this point as x sub 3 star. Remember, we get to pick anybody we want, any number we want in that interval. So take a look now. X sub 3 star lies between x sub 2 and x sub 3. So 3 matches 3. This is 3 minus 1. 2. 2 matches 2, right? I'm looking at the subscripts now. 2 matches 2. This subscript is 1 less than this one. 2 minus 1. 1 matches 1. This subscript is 1 less than this one. 1 minus 1, 0. So let's go back over here. I matches I. This subscript is 1 less than this one. That's what he's telling us right here. He's just telling us, if you want to find x sub I 19, let's just make it a 19. You're going to find that between x sub 18 and x sub 19. He's just wanting us to understand where each of these sample points lie. He doesn't want us to think that 2 of them could be in the first interval, 3 of them in the second, etc., etc. There's 1 per interval, and this is the rule on where they live. Okay? And now we get to then. Then's always a, that's a happy word when you're writing a long definition because you know you're getting close to the end. We've written all of this so we could get to the then, the definite integral. So here we go. We've written all of this, which is the definition of the definite integral, so we could get to this. Then the definite integral of f from a to b is. And this is our notation. Okay, this is our notation. So we'll write this in a bolder pen. We write the integral. Well, let's just write all the symbols down and then we'll learn how to say it. This is our symbol for the definite integral. Right? This is our symbol. Let's pick a different color. We call this the integral symbol. All right? And we read this, if we were going to say the words, we say the definite integral of f from a to b. From a to b. We refer to a as the lower bound. It is the left-hand side of our interval. It is the lower number. A is a smaller number than b, so we refer to it as the lower bound. We refer to b as the upper bound. The function that we're integrating, we call that the integrand. Okay. And for now, for us, we're going to think about dx as being part of the integral symbol. As we move through calculus, we'll begin to understand what this means, but we're going to think about it as being part of the integral symbol for now. So those are all the parts of our definite integral. We would read this again as, once we see this and we see a lower bound and an upper bound, we would say that's a definite integral of f of x from a to b. Or we could say the integral from a to b of f of x. That's another way you may hear this expressed. The integral from a to b of f of x. Okay? Now what is that integral going to be? Well, it's going to turn out to be exactly what you and I thought it was going to be way back here, because we've already written it up here. It's going to be the limit as n goes to infinity. Okay? And then we're going to add, so we're going to use a summation sign to represent that. We're going to add, and what are we going to add up? Well, we're going to add up a bunch of heights times a bunch of widths. Because, in essence, you and I have already learned in section 5.1 that we're adding up a bunch of rectangles. The area of a bunch of rectangles added together is going to be the area under the curve. That's what we discovered in section 5.1. So now we need to make sure we specify to the person reading this how we're determining the height and how we're determining the width. Well, we've already told them that we're going from I equals 1 to n. We're going to have n of these rectangles. So this is going to be x sub I. Now, if I was using only the right-hand endpoints, I would just leave the x sub I here, because now I is 1, right-hand endpoint. I is 2, right-hand endpoint. I is 3, right-hand endpoint. But that's not what we said. We said the endpoints aren't that special to us. We stated that right here in black. We said, you know what? Because the intervals are so narrow, you can use any number you want to determine the height. And so we're going to say that this is x sub I star. Now, again, let's make sure we haven't lost, the forest for the trees here. But let's remember, this is our height, and this is our width. And all we're saying here is we're going to take the area of the rectangle, height times width, and we're going to add up all of them. And then we're going to let the number of them go to infinity. The order of operations is important here. We're going to find this first, like we did in section 5.1. Then when we took the limit, once we took the limit of the example I did in that video, we got 1/3. So we do this first, and then we take the limit second to get our numerical value. Now, we just have to add one more caveat here. Provided that this limit exists. And that, I told you it's going to fill up the whole board, that is our definition of the definite interval. That is what we are going to do in section 5.2. We're going to use this formula to find the area under the curve. So we have the integral symbol, we have f of x is the integrand, this is the lower bound, this is the upper bound. And if you look at this side, just look at this side, and then look at this side, you see some similarities. Here you see an f of x, here you see an f of x, here you see dx, you see delta x, all right, very similar. F of x, our integrand, does represent our height. Dx, we can think of that as representing our width, and so this still looks like height times width, right? Height times width, that's what it looks like. So, if this limit exists, we say our function is intervalable. It's a word, you can use that in, hangman with your friends and probably win a few times in a row before they figure out that's actually a word, but it is a word, all right? Now, you're going to hear this phrase, so I'm going to introduce it right now. This, something that looks like this. What? Let me redraw this. There. Let me get that, my bubble. I got kind of carried away with my bubble. There. Sums of this nature, right? Sums of this nature inside this purple. We call these Riemann sums. So you'll hear that phrase, and you may see it in your book. That's called a Riemann sum, named after a German mathematician. And so if you hear somebody saying Riemann sum, this is what they're talking about, this sum right here, okay? So where are we going to go with this, and what are we going to do with this, and how is this going to make our lives better? Well, it is certainly going to make our lives better. One of the things that's not going to make my life better is I have to erase all of this wonderful work. So to make room, I'm going to go ahead and erase this. I'll refer back to it. It's in your textbook, and we'll make comments about it as we move through the rest of this section. But unfortunately, to make room to do the rest of the lesson, we have to eradicate that from our whiteboard. So it's been eliminated. Right? So where are we going to go from here? Well, we need to have an understanding, right? An understanding of what that all meant. How does that help me move forward? And so let's just draw a couple of pictures, all right? And we'll start with, we'll just start with a picture like this. Let's just start with a graph that, we'll draw something like cosine. We'll pretend this is cosine. This is 2 pi. This is 0. This is y equals cosine x. And now, when we get a function that looks like this is the first time we've considered this. We've mentioned this in passing. What's going to happen if our function goes below the x-axis, right? Well, how are we going to handle that? What are we going to do? Well, here's what we're going to do. We know that this is an area right here. And we don't know how to find it specifically because it's cosine. We don't know what that area is, but we know it's the same as this area because of symmetry and pre-calc. We know those things are symmetric. We know those areas are the same. We also know there's a relationship between those areas and this area right here. Now, how are we going to express areas above the x-axis versus areas below the x-axis? What are we going to do? If you'll allow me to name all of these areas, I'm just going to call this a sub 1, I'll call this a sub 2, and I'll call this a sub 3. I think all of us, based on our pre-calculus knowledge, are very confident that this is a true statement. Those have the same area. We know that the area under the x-axis in one period of cosine is going to be the same as the area above the x-axis because of the symmetry. It may not be on my graph because I didn't draw it very carefully, but we know that to be true. So what are we going to do in calculus? How are we going to have a conversation then about the areas above and the areas below? Well, it's pretty simple. We're going to acknowledge, right? We're going to acknowledge the fact that my function takes on positive values and negative values in the context of area by putting a minus sign in front of the area that occurs below the x-axis. Okay? That's what we're going to do. Now, we're not saying area is negative. That's not what we're saying. We're not saying that at all. We're saying if we were going to have a conversation about these three areas, right, we would have it like this. We would say that the total, right, the total area is equal to a1, it's above the x-axis. We're going to put a minus in front of a2 to represent the fact that it's below the x-axis. And we're going to put a plus in front of a sub 3 to represent that it's above the x-axis. So we can think of this as net area. Now, we have to do this, okay? We have to do this because of the following fact. If we were to, we have cosine here, we know our function. If we were to use the notation that you and I just adapted, if we were to ask ourselves, what's the integral from 0 to 2 pi of cosine x dx, right? We don't know how to find this. We really don't. We could draw our rectangles, we could do it, but we really, unfortunately, because of the function cosine, the algebra that we have at our disposal is not going to let us do this limit. So I'm not going to write it out as a limit. But what I'm going to tell you is, eventually we're going to learn how to find this. And when we do, the answer here is going to be 0. Okay? And we'll get to that. Maybe not in this video, but we'll get to that fact. The answer is going to be 0. And why is that when we're thinking about this as area? Well, this is where the definite integral and our approach to talking about the definite integral as area, it gets a little foggy. We have to understand that integrals are integrals. Integrals are not area. That's the way you and I are introducing the concept of an integral. We're introducing the concept by saying, well, let's think about integrals in the context of area under the curve. But an integral is an integral. It's not an area. It's an integral. But it's something that we can visualize in the beginning by attaching to it this familiar concept of area. And because we've done that, then when we get to a situation like this, we tend to run into a bit of a bump. And the bump is, all right, area is positive always. It has been our whole lives. So I have this area, and I have this area, and I add this area. And if we think of area as being positive, I understand the concept, the physical concept of area is positive. You can't draw a box that has, or a rectangle that has a negative area. But it runs into a bit of a roadblock when we try to firmly just attach area to the definite integral. So what do we have to do to overcome that? The integral is going to tell us this integral is 0. All right, that's the mathematics. The mathematics is going to tell us 0. If we want this to be area, we're going to think of this as 1 piece, 2 piece, 3 pieces. And we're going to think area is always positive, and we're going to expect a positive number there. We're not going to get a positive number there. We're going to get 0. And the reason we're going to get 0 is integrals are not area. Integrals are integrals. We're using area as our learning tool to help us visualize an integral, a definite integral. So you and I have to make the adaptation. We have to make the adaptation, and we have to say, okay, if I'm below the x-axis, I'm going to put a minus sign in front of that area. Okay? And again, no one's saying area is negative. We're just saying below the x-axis, we're going to put a minus sign down there. All right? That's what we're going to do. Now, we get a theorem, right? Continuing with the section. We get a theorem. And what does that theorem say? We'll just draw this theorem over here. Because I don't want to erase right now. This theorem is not really related to what we were just talking about. So what does this theorem say? It says, well, if f is continuous. Now remember, our definition did not require continuity. If f is continuous on A to B, or if f has only a finite only a finite, a number of jump discontinuities. All right, so now we're saying maybe our function is continuous. Or if it's not continuous, it has only a finite number of jump discontinuities. Then f is integrable on A to B. All right? i.e., the definite integral exists. Now remember, exists means is a number. How about results in a numerical solution? Okay. So that tells us when we're going to get an answer to our problems. We're going to get an answer if our function is continuous or if it only has a finite number of jump discontinuities. Now, if you're asking yourself questions like what happens if it has an infinite number of jump discontinuities, or what happens if it's not continuous, those are questions that are quite interesting, and if you want to major in mathematics, you can find the answers to those down the road. They're not going to be questions that we address in a Calc 1 class, however. Okay? So, from here, we get a pretty important theorem. So I'm going to go ahead and erase this picture. And our theorem is as follows. Okay. If f is integrable on A to B, then what? Well, then the integral from A to B of f of x dx can be found by taking the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x, where delta x is our width and x sub I equals a plus I delta x's. Just write that down. I'll make it all make sense. Now, how is that different than the definition we wrote down just a few minutes ago? Well, A, it's shorter, but it's not the definition. It's a theorem. Theorems are always shorter than definitions. Well, that's a huge, huge generalization. What's different about this? Look right here. There's no star. This is x sub I. This is x sub I. What is this theorem saying? It's saying if you have A to B, and you have x sub 1 here, now remember that's x sub 0, and you have x sub 2 here, and you have x sub 3 here. Out here somewhere is x sub I. This is x sub n. Right? That's what we said. This theorem is saying you don't have to use sample points if you don't want to. X sub I is a right-hand endpoint. what the theorem is saying is we can use right-hand endpoints. Okay? We can use right-hand endpoints. We don't have to pick our... Now, why would we want to pick right-hand endpoints instead of arbitrary points? Well, we're going to pick right-hand endpoints instead of arbitrary endpoints. And now our book chooses right-hand endpoints here. Perhaps your textbook chooses left-hand endpoints. So everything I'm saying about right-hand endpoints in your book would be left-hand endpoints. But our book chooses right-hand endpoints. Why would we settle for right-hand endpoints when we can choose any point we want inside of here? Well, the answer is we're going to need patterns to make these work. Similar to the example we did in section 5.1, where we found the area between 0 and 1 of under the curve y equals x squared. We used very specific patterns to find answers. We're going to have to do that again. And the only way we're going to find simple, easy to determine patterns is to eliminate the idea that you can choose any point you want arbitrarily in any interval you want. We need a very regimented, consistent approach. And our regimented, consistent approach in our book is going to be to use right-hand endpoints. Okay? Now, where do we go from here? Well, we're going to clean this off. And we're going to talk about some things that are going to make doing the homework a little easier. Okay? So let's go ahead and erase this. The homework is going to come down to pattern recognition. Right? And I'm going to do another video for section 5.2 where I solve some homework problems. I didn't do that for section 5.1, but I'm going to do that for section 5.2. So here are some formulas, some pre-calculus ideas that we may have forgotten that we need to remember before we can make good progress with our homework. In pre-calc, we were taught what happens if we add up the first n integers. This says I goes from 1. There's a summation, so that's plus. This is my index, I, so my next number is 2. My next number is, after 2 is 3, and this continues until I get to n. And in pre-calc, they taught us, in math induction, in the section that was about the binomial theorem and mathematical induction, we learned a formula for this. We learned this was equal to n times n plus 1, all divided by 2. If somebody says to us, here's an example, right? If somebody says to us, I equals 1 to 50, what does that mean? That means they want us to go 1 plus 2 plus 3 plus all the way to 50. Well, they don't expect us to add up those 50 integers. They expect us to use this formula, and they expect us to say, okay, well, that's going to be 50 times 50 plus 1, all divided by 2. Or that's going to be 25 times 51, right? And for every 4 25s, we get 100, right? 4 goes into 51. 4 times 12 is 48. So that's going to be 1,200. That leaves us 3 left. 48, 51, 3. And that's going to be 75. So this is going to be 1,275. Right? So we need to know that formula. Related to that formula is the formula that we already used in the video on section 5.1. What happens if I add up all the squares? 1 squared, 2 squared, 3 squared, 2n squared. Okay. Well, the formula for that, as we already wrote in section 5.1, is n times n plus 1 times, well, that's wrong, 2n plus 1, all divided by 6. I'm not going to do an example of that. You can do the arithmetic. So this is a formula we need. This is another formula we need. a third formula that we're going to use in our book is what happens if I add up the cubes. 1 cubed, 2 cubed, 3 cubed, all the way to n cubed. Well, this formula is n times n plus 1 over 2. And when you're looking at that, you're thinking, well, we've already got that formula. Well, it's n times n plus 1 over 2, quantity squared. Okay? Those three formulas are going to be key to doing your homework problems quickly and efficiently. Now, what else do we need to remember from pre-calc? Well, we need to remember some of our sigma notation that might have escaped us. Like, for example, if we have I equals 1 to n of a constant c. What does that mean? That means c, when I is 1, there's no I here. So when I is 1, when my index is 1, I just get a c. When my index is 2, there's still no I here, so I get another c. It's a constant, and I get another c. And this keeps going until I get to my last c. And if we think about this, there are n c's, right? C plus C plus C plus C, n times. That's literally the definition of multiplication. That is n times c. Some of the other formulas about the sigma notation that we may have forgotten from back in pre-calc is what happens if you have a constant times something that your index does impact, right? This is a sub I. What does this mean? This means c times a sub 1, c times a sub 2, c times a sub 3, all the way down to c times a sub n. And if we think about that, we can factor out a c. And that would be a sub 1, a sub 2, a sub 3, a sub n. And so that turns out to be c times the sum I equals 1 to n of a sub I. So what does this say? It says we can factor a constant out of summation, all right? And then the last one, we'll squeeze it right down here. The last one that we need to be aware of is what happens if you're adding or even subtracting two different things. And what we said back in pre-calc is we could split this into two different sums. I equals 1 to n of your a sub i's plus, right, the sum I equals 1 to n of your b sub i's. And it also works for minus. Okay? So those are just a quick review of some of the formulas dealing with sigma notation from back in pre-calc that we need as we move through this part of the calculus textbook. Okay? All right, so where does the journey take us next, right? Where do we go next in section 5.2? Well, to be perfectly honest with you, there's a lot of section 5.2 left. So I am going to stop the video here with that summary of some of the pre-calc formulas that we need. We're an hour into this video at this point, and I'm going to go ahead and stop the video here and just pick up in a second video. I don't want to put together a 2-hour definite interval video. So we're going to call this section 5.2, part 1, and we'll pick up the rest of this lecture in section 5.2, part 2.